Now let us see how to solve this problem. This is also a cantilever beam of span 12 feet, and we have a load of 5000 lbs at a distance of 6 feet from point A, and we have this load. We can call this as a trapezoidal load, or we can call this as linearly varying load. If you call this as a trapezoidal load, I can say this is starting with the value 0, ending with the value of 1500 from 6 feet to 12 feet. I can give from and to distance of a trapezoidal load. There is no need to break this member into two beams. This load, I can give this as a member load at a distance of 6 feet. This one I can define this as a trapezoidal load from 6 feet to 12 feet. That is one way of solving it. And another way is to define a node here, give this load as a nodal load, and then define this load as a linearly varying load, or even as a trapezoidal load acting on the full length of the member BC. Now let us see how to solve this problem. Now the units here are lbs and feet of the screen. How do we understand this? If you see the right side bottom, you can see the input units is lb and feet, and you can see this coordinate here. You can read the coordinates here. X is 10, y is 0, z is 0. So this is 10 feet. Now we can say edit, and we can increase the lines by 12. Now we can draw this as a single member initially, and I'll close this grid. I'll define some property. I'll say 1 feet by 0.75 feet, and then I'll give this to this beam, and I'll define a fixed support, give it to the concerned node, and say assign. Now let me give the load title. I'll pick this load case 1, and now I'll go to member load. Concentrated force, the value is 5000 lbs at a distance of 6 feet. So this is minus 5000 lbs at a distance of 6 feet. I'll say enter. Now I'll go to trapezoidal load, starting value 0, ending value minus 1500 lb per feet from 6 foot to 12 foot. And I can say enter and say escape. Now this one I'll give it on this member. So we get something like that in the middle. And this trapezoidal load also I'm giving on this member. So this is how we get this loads. Now I can say analyze, add, and I can run the program and say done. Now we can go to post processing. So this is how we get the deflection. Now the question is, find the deflection at B. For that, you can pick this beam cursor, you can double click this member, or you can say properties, deflection in Y. You can type 6 feet here. So the displacement is minus 10.934 is the deflection at 6 feet distance. So this is one way of understanding the deflection. The value is 10.934 millimeters. Now we'll solve this problem in some other way. I'll remove these loads. I'll say delete this one, and even this also I'll delete. Now I'll break this member into two pieces. I'll say add node at midpoint. I'll say OK. Now I'll say labels, node points. Now we have a node point here. Now I should define the 5000 lbs load as a nodal load. So I'll do that. I'll say enter, Let me see whether it got added. Yes, it has come here. Now the second load, that is this one, I can define that as a linearly varying load also. Let us see that. It is a linearly varying load starting with 0, ending with minus 1500. I'll say enter and I'll say escape. Now this particular load, I'll give it on this particular node. I'll say assign to selected nodes. I'll say assign. Now this one, that is linearly varying load, I'll take the beam cursor and give it on this particular member. Now that is how it is. Now we can analyze this problem having changed the loads, and you can go to post processing, and this is what you have. And you can place your mouse here and it will show the displacement in Y. This is minus 10.978. Earlier the displacement is 10.934. Now this is 10.978. So this deflection must be most accurate because we have defined a node at the point of our interest. Now this is one way to find the deflection. Another way is to go to results and say view value, nodal, global Y, and say annotate and say close. So like this you can find this deflection. There is another way of finding the deflection. You can switch on the deflection diagram. Now we have finished solving this particular problem, and then let us see, or let us discuss how to solve this problem. This is a beam of span 12 feet. You can solve this by two methods. You can draw this one as a single member, and you can give this 8000 lbs at a distance of 3 feet and this 8000 lbs at a distance of 9 feet. So these two things you can give them as a member loads. That is one way to solve. And then to find the deflections at B and C, you can double click the member and go to deflections at the last icon, and you can type 3 feet so that you will get dy, and if you type 9 feet you will get the deflection in Y at a distance of 9 feet. That is one way. Another way is to draw this beam as three members, 3 feet, 6 feet and 3 feet. That is, draw this as three analytical members and define these loads as nodal loads, and then you request for nodal displacements at point B and C. So this way you can solve this problem, and we will learn more about the 3D structures in the coming classes.